Hello everyone. My name is Shomodeep Chaudhary and this is Sai Teja. We are from IIT KG Kharagpur. We are here to talk about a research paper called code2vec, Learning Distributed Representation of Code. This paper has been authored by these four authors present here. And to begin with the presentation, we have Sai Teja, who will be starting with the presentation. Sai Teja, please go on.
Yeah. Our code2vec model is going to take the input. It is going to take program as an input. It can be any program, and it is going to give the property of the code. So this property can be anything. Basically, what it internal does is like given the code, it is going to generate the embedding of the code, like a basic representation of this code. Using that representation, we can do any task like predicting the description of the code, understanding and getting the details of the code, or generating or something like if the code contains any malware or not. You can do any general task using that embedding. This is the basic purpose of this code. Yeah, here is a basic motivating example. So eh, this is a code. If you have to tell what this code actually does, we need to understand the code line by line. Like if you detailedly observe the code, we can tell that this code is performing the reverse operation. So if we supply this code to our code2vec model, it is going to tell that this is reverse array operation with a probability of 77%. And uh, we are just predicting the function name of this code. So in order to train this code2vec model, we are going to have this, we are going to need millions of examples of these pairs, the program and the corresponding property name. Uh, in this research paper, they have performed this. They have taken all the methods of Java library, Java programming language, and they gave input as that code. And for truth value, they kept the function property name as the truth value. So given the code, the code2vec going to generate the property name. And for after training of our model, for any code which is not seen till now, our code2vec model hopefully going to give the corresponding property name, like valid property name. Next slide. Yeah, it is big. Can you go to the last slide? Yeah, it is basically what internally what it does is we are going to have a neural network, and which is going to capture all this knowledge. Like internally, it performs some operations so that it is basically generating the. As you can see, there is a code vector. That code vector is nothing but the embedding of the code. Using that code vector, we can given that code vector, we can perform any activity. Here we are going to predict the property name. So, yeah, like I was saying, the research paper in this research paper, they have taken Java programming language, and they have taken all these methods as core input, and they mask this function name, property name, or method name, and they are predicting that method name. So and this is going to work for many. They made sure that it's going to work for any programming language. And this is one of the basic tasks we can do given a code like. But in general, we can do all these tasks like general. We can do malware present or not. or we can tell what we can predict the required dependencies of the code, or keywords, hashtags, or clone detection. We can do all this. So how does this code2vec work? Let's look at. It is nothing but a neural network. Here, neural network is a sequences of simple algebraic functions over vectors and matrices. So, as an example, I'm going to take a simple like this sentiment analysis. Like given a sentence, we are going to predict if it is a positive sentence and the native, or it is a native sentence with a score, with a confidence of. So I'm giving a good talk. It is small sentence, a good talk, and for each word, we are going to have these embeddings. These embeddings are nothing but vectors representing that word. So these embeddings might come from an external network, or what we can do is that we can initialize these embeddings randomly initially, and along with the training, we are going to update these embeddings so that we get a good representation of the embeddings. For after training, these embeddings going to have a meaningful representation of the word. Like they are going to capture the semantic properties of the word. So what we give so first initially we are going to initialize them randomly, and we are going to perform some mathematical operations like we can do average, and we can transform that vector with some parameters with parameters here w, and for predicting the score we are just summing up, like as I was saying, we can do many operations. uh, so we are going to predict the score, and from our we are going to also have this uh, truth values from our hierarchical function. Using this predicted score and truth score, we are going to calculate the loss, how much error we had made. Using that error, we are going to backpropagate and update our parameters according to, like if it is has much larger error, we are going to update the parameters more, or else along with the parameters, as I was saying, we are going to also update the vectors, these embeddings of the words. This is basically how a neural network works. Now coming back to our problem has now two challenges, the main two challenges. The thing is, we at input level we have code. Now we have to convert this, decompose this code into a smaller building blocks, so that each building block has a some meaningful representation of it. So that these challenges will be covered in detail by Somjit. So some and we are going to each building block. We are going to aggregate all these building blocks to get a code vector of the input code that we are going to see in the coming slides. Next, okay. This is a high level overview of the what I was saying regarding code2vec. So given a code, we are going to decompose all this the code into multiple small building blocks, like some representation of this code, and e each of these building block we are going to represent them as a vector, and these vectors are again first initially randomly initialized, and along with the training these are updated to get again capture the semantic meanings of the, and we are going to aggregate all these vectors to form a new vector which captures all the meaning, all the knowledge of this code. So this small code vector, the final code vector, is going to capture all the meaning of this, all the details of this code. this is called in paper it is called as code vector. And using this code vector, we can do any task. Uh, for example, we can predict the function name, or we can detect if the code contains malware or not. Uh, from here, Samriddhi will take.
So as Saiteja mentioned, there are two challenges. The first challenge is decomposing the program into smaller blocks. So initially the input is a program. This program can be initially fed into the code2vec model, or it can be further broken down into further analysis. We can further analyze this program and feed the analysis part into the code2vec model. If we simply feed the whole program into the code2vec model, then the model would have to put in lot of efforts in learning from the program and then apply the code2vec. If we do various analysis and then feed the analysis part into the model, then the model would be doing language specific or task specific tasks, which is not required. Hence, we need a trade-off between learning rate and the analysis effort. And to to get a sweet spot, we have found the paper has found AST parts to be the trade-off, proper trade-off. Now, what these AST parts are? So, a program when we get as an input to the model, this program can be considered as a set of different AST parts. As we can see in the left part, there is a small program mentioned, and this program can be written as a AST part, which is mentioned towards the right. This program consists of various AST parts. If we specifically look at one AST part, which is the blue line, we get done. After done, there is symbol ref, then unary prefix, then while, if, assign, symbol ref, and again done. This is one path of this program, and there could be various such paths. So as it is mentioned, AST parts capture various semantics by just using the syntax of the program. Now, as mentioned, there could be various parts of this program. The next task is to take this AST part and form a small building block. So as I mentioned, we are going to represent the AST part as vectors. So this is one path which I had mentioned in the previous slide. Now we see that there are two token vectors. There are two tokens present which are done, and rest are basically the paths. We take these tokens and get the token vectors, and also for the paths we get different path vectors. We concatenate them, and then using a neural network we get a path context. This is basically a fully connected layer which we use to get a path context. But this path context is for a specific path. As I mentioned, a program would have various such AST paths. We take different AST paths and get the path context of all the AST paths. After getting the path context of all the AST paths, we now need to aggregate all these path contexts. So the next challenge what I'm going to talk about is aggregating all the set of path contexts which we have generated. There are three possible ways to aggregate. First is to take the most important vector. So, this is not a right way of doing, because we'll be missing out on other vectors which are not as important as the most important vector, but these are still important to predict the property of the program, or maybe required for any other tasks which we are supposed to do with the code2vec model. Second method, which is mentioned, is using all the vectors and simply averaging them. And similarly to the previous method, this is also not the right one. We may still not be able to achieve important vector, since every vectors are given same weightage, which is not the right way of aggregating all the path contexts. So the third and final way to aggregate this set of path contexts is using attention. So attention is a learned weightage average way of taking all the path contexts and using the attention vectors to get a code vector. So what attention does is, there is a attention vector. This attention vector we use to get to do dot product with different path contexts present, and we get a particular value for each path context after doing the dot product. These values needs to be normalized. So we use softmax to get the normalized values of normalized attention vector values for all these path contexts. We then use these values to get the weighted average of the path context and sum it over to get the code vector. This code vector, as I mentioned in previous slide, is a learned weighted average. On doing so, we are getting the semantic meaning of each of the path contexts. So basically, we can say is more the attention, more important is that particular path for predicting the property. So as it is mentioned in the slide, the amount of attention this path context should get is basically depending on uh, the attention, the importance the path context is towards predicting the uh, final property. Now about the code2vec architecture. So we initially have a program which is an input. We take different bag of context, that is converted into different tokens and the path vectors, concatenate them and send it to a fully connected layer. So after decomposing it, we get different path contexts. These set of different path contexts can be aggregated using attention vectors, and after doing everything, we get a code vector, which is a representation of the program. And this representation of the program can be used to predict uh, different tasks. Now, the experimentation done in this research paper, they have used a training set of around 14 million examples, and the total training time it took was less than 1 day, which was very fast because of its simplicity. And the entire network was trained simultaneously. This is all about the experimentation which was conducted. Next, we have Saiteja, who is going to take over.
So, yeah, I'm going to show these two examples of codes. Like if we supply these codes as input to our code2vec model, now we are going to have like some this has mentioned. We are going to generate all the path context, and we are going to aggregate them using the attention. And this is the if you see observe in the left code, like these are the top most attended path contexts, like path contexts which have um, more attention bits, most attention bits. So if you can see here, there is a red, this red path context has more width. This width correspond to the attention bit. The more the uh, width, the more important it is. Like this red path context is acting as more important. It is so this if you observe here, like we are emphasizing on this return true. This if you this is this code belongs to contents method. So here we are focusing on returning true in contents method. Similarly, if you look at the right side code, it is getting get method code. So it is focusing on, if you look at the attended paths, this path context, the most attended paths are this returning the element. You can all it is iterating over the objects. These are the most important path context here. So using what I'm trying to convey is that using this attention, we can know which paths are important. So which parts are playing a major role for this code. Next, uh, like I was saying, this is the AST paths of the AST tree of the code, uh, the previous code. So if you observe here, in for each block, this red attention path, this path context has more attention. This width corresponds to the attention weight. So more attention weight means it while aggregating, it is taking more role. So it is going to have play an important role. Since it is a contains method, whenever we are checking if the keyword is present in the array, we are going to return true. That is what it is uh, seeing actually. It is this attention acts as an interpretability. Like most of the neural network codes are not interpretable, but this is a nice result actually. Because of this attention, there is some interpretability we can observe, like which are the paths which are important by that we can know by this attention. Next. Now, this is so as part of our code2vec model, we are going to yeah, as part of our code2vec model, we are going to have embeddings of these labels as well. Like we are going to map every code to a code vector, and from that code vector to a property name. Like according to the paper, we are going to take this task of creating property name. So each property name will have some embedding, which are learned to use as part of our code2vec model. And these learned embeddings are embedded here, like all the embedding. This is the embedding space of these learned labels. Now you can go to the next slide. Yeah, can you? Yeah, if you look into this embedding space, these learn they are actually like nicely learned. Like whichever property names which are similar, they get close together in this embedding. This is what we want. Like the semantic meaning of the property name is preserved here. Like you can observe the get accounts, get account number. These are closely linked property names. Now the embeddings of these all these things are very close. This is a nice effect of this code-vec algorithm. Now, if we go to the next slide. Now, since we have these embeddings already, the learned embeddings of our property names. This website is available. You can everyone can try this. So, given a word, we can get uh, what are the most similar property names of that word. Like here we are giving count as a word. Now this count going to have an embedding, and out of all the embeddings present, which one is close to that, we can what it internally does is it is going to compare the embedding of the count and with all the embeddings of the property names, and return the which has which is very less, which is very close. That is get count going to have very close. And this is another interpret like nice effect of this code-to-vec model. Like we are going to have, like I was saying, we are going to have embeddings of this equals property and two lower property. Now we can combine these two property names to get the property name of which have the uh, uh, like result of combination of these two properties. Like if we do if we perform this equal operation after performing lower, this is nothing but we are doing the equals ignore case operation in Java. Like this is based on the Java property names. Like that's why we are good. Like internally, what it does is we are going to have embedding of this equals property, and we have embedding of this two lower property. When we perform this AND operation, it basically performs the addition of this embedding, and it will return the property which is very close to this resultant embedding. That is equal ignore case is having very like it is very close to the resultant embedding. And we can also perform this analogies like receive is to update download. Now receive is a property name, and download is a property name. So what it does is like it is going to subtract receive from download, and it is going to add to send. So if receive is download, then what is send it will basically correspond to upload. That's these are something like small analog since we have this embeddings. And this is in the website we can also perform this. Like given a you can write your own code here, and you can get the AST pass of that code. Also, the code2vec prediction of that code. It is going to predict the description of that, like the property name of that method that you have mentioned. Yeah.
So here is an open source about the code present. If you guys want, you can have a look at it. I've just taken a screenshot of it. Next, we finally to summarize everything. So the core ideas in learning code snippets is basically representing a code snippet as a set of synthetic parts, and then use aggregating all these parts using attention. This is a basic. The code2vec is basically a simple and a fast to train architecture, and we can also see how the attention mechanism was, and how interpretable this attention mechanism is, and the learn vectors which we have under captured has is can be used for the various tasks which Sai Teja has mentioned, like getting analogy, getting analogy, or getting different representations. So to sum up, these are the summaries, and if anyone is interested to get to use this code2vec model, they can simply use this link which is present here, and basically try out different snippet of codes and get the various results or properties which they want. So that's all from us. Thank you.